Good morning and welcome to this fourth lecture under Adaptive Signal Processing module. In this lecture, we will briefly look at and continue what we discussed in the last class, which is the Wiener filter or Wiener filtering. So, we will look at an example and just try to see how Wiener filtering is applicable to this specific example. It's just a simple example, but hopefully that will give you some sense of what the Wiener filter can do. So we will look at yesterday in discussion we had looked at how to obtain the optimal filter, which essentially was an FIR filter depending on the input signal X, and assuming that input signal is corrupted by some noise. If we are interested in designing this filter, that filter's coefficients are denoted as W. So the expression we had derived was this inverse of the autocorrelation matrix times the cross correlation vector RDX. Right? So this is what we want to apply, and the problem we are considering is, let's say, just a simple filtering problem where the observed signal is X of n. This observed signal essentially is a sum of our desired signal with some noise. So we can think of this as the desired signal being corrupted by some noise, and that's what we are observing, and we would like to design a filter to remove this noise. One assumption we have is that this V of n, which is the noise, is zero mean and is uncorrelated with D of n. As I had mentioned during a discussion on random process, many practical scenarios, this is not a difficult thing to expect. Typically this noise is uncorrelated with D of n, but there could be some other noise like terms which could be correlated with the signal, and that would require a different kind of analysis and understanding, which we are not worried about right now. Okay. So let's move on, and knowing from our previous discussion the optimal filter, let's say I'll denote this as W optimal, will be this R inverse times RDX. So these are things which we will just look at. How do we get these? Again, remember that in this case we are assuming we know some statistics of the signal and the noise. Right? So if you look at this cross correlation RDX of k, it's the expected value of the D of n desired signal times the input signal xn minus k. Right? And this we substitute for xn minus k from what we know about the observed process, and substituting that, we see for this case, since the desired signal and the noise are uncorrelated, our cross correlation is essentially the autocorrelation of the desired signal, which is RDD of k. Right? Similarly, we can look at the signal X and find its autocorrelation, because we are interested in finding this RXX inverse, right? Which means we have to estimate each element of this RXX matrix depending on the length of the filter. So again, substituting for x as d of n plus v of n and xn minus k as d of n plus bn minus k, assuming uncorrelatedness between the d and v, we could see that it's essentially RDD of k, which is the autocorrelation of the desired signal, plus the noise signal. So this result here, which essentially says autocorrelation of the signal is sum of these two autocorrelation holds when these two signals are uncorrelated. Okay. So this is kind of a general rule which happens in almost all cases when there is uncorrelated signals being added. The resultant autocorrelation is just their sum of their autocorrelations. Okay. So given this RXX and RDK, we can now try to find what should that filter be, and if we assume that filter to be of length m, then that will have these coefficients W0 to Wm minus 1. We could use this W as R inverse RDX. R is a matrix which we could form from the RXX equation we had, and then accordingly RDX is also a vector for all this m coefficient length, and then this is just essentially finding this inverse, then multiplying with this RDD, right? So this kind of just illustrates that for a simple filtering problem where the signal is corrupted by noise, how do we go about obtaining this filter, right? So now let's just kind of continue this example with some specific setup, and that I just refer for convenience as example 2, but note the setting is very similar to what we have in this example 1. Okay. So what is this setting? So the setting which we are interested in this problem is, we assume something little more specific on the desired signal. Let's say the desired signal d of n is an AR1 process. For those of you not familiar with what AR means, AR is essentially an auto-regressive process. Just to kind of say a little bit more about what this auto-regressive process, you could think of this AR, in this case let's say AR1 process, as let's say a system which is, let's say, of this form. For z minus 1, it's like an all pole filter whose if input is, let's say, white noise. We have white noise as input, and let's say unit variance. Then the output is so in this case this is our, so this is how we assume that d of n is obtained, right? So once you know this, if you know what alpha is, you could relate the power spectrum of the output to the input power spectrum through the filter's magnitude response. So that's just a brief on what AR1 process is. So coming back, if you go and look at the autocorrelation of that process, which is again in this problem, either you could give an AR1, given d of n is an AR1 process, you could again find this autocorrelation, or in this case let's assume that the autocorrelation is given to us and it is of this form. So note this is a decaying term on both positive and negative case, and this is kind of typical of an AR process, right? So this alpha is some quantity which is between 0 and 1, and the more closer it is to 1, this pole is more closer to the inner circle. So far away it is from 1, it's more closer to the 0. That's kind of the indication. So now coming back, so we again go back and look at what V of n. V of n is still uncorrelated with D of n, and we assume this V of n to be white noise with variance sigma v square. So this noise is corrupting our D of n, and we are interested in finding, as in the previous case, a filter W. Let's say in this case we are only interested in finding a filter with 2 coefficients. The reason we want to just look at 2 coefficients is just to kind of illustrate how this kind of problem simplifies to something which you can easily interpret. So moving on with this setup of D of n being an AR1 process and the noise being uncorrelated with it, let's see what happens to the W which we had estimated in the previous case. So we go ahead and do similar things as we did in this previous example. Again, given the uncorrelatedness between the desired signal and the noise, this Rxx is just sum of these Rxx. Rxx is sum of RDD and RDB, which will again show up in your autocorrelation matrix. And similarly, if you go and evaluate, assume that this desired signal has unit variance, then that's RDD0 is this and RDD1 is alpha. And RDX, which is the cross term, is also same. That's how we derived in the previous example, since this RDD is same as RDX, given that D and V are uncorrelated. Right? So with this setup, what we have for the autocorrelation matrix is a matrix of this form, which is 1 plus sigma v squared alpha, alpha and 1 plus sigma v squared. So you can see that this matrix has this structure which we discussed yesterday, given this is a wide stationary process, that it has a diagonal which is all same, and again of course it's a 2 by 2 matrix, it's symmetric, Hermitian symmetric if you want to think, and this alpha, if we extend it, will be alpha throughout and similar. But for our case we are just restricting to a 2 by 2 matrix because we are interested in a filter whose length is 2. Correspondingly, this RDX is 1 alpha, and if we do find the Rxx inverse, that is if you assume this, not assume, if you find this Rxx inverse times Rdx, you could find Rxx inverse and multiply that with this term Rdx here. You will see that you have a weight vector of this form. Note the weight is a vector, that these are the two coefficients, and there is a common denominator term here, which is what is represented here. So, another way to look at the filter coefficient is just to write it as in Z transform or in terms of Z. So, the denominator term here is essentially this denominator. The first term is this 1 plus sigma v squared minus alpha squared plus alpha sigma v squared z, right. So, this is like the Z or minus 1 term, or you can think of this as the 0, you can find the 0 of this polynomial by making this equal to 0, which will be some function of this alpha and 1 plus sigma squared. Right. So, again what do we see here? It is just say that these relations we knew already, we are just plugging in these values for alpha sigma v squared and we end up with a filter which is of this form. Okay. So, this just can be thought of as a filter, but let us just now try to find out what did this filter really do. So, we are taking this signal, we are using this and estimating a desired signal which is a d hat, and let us see what happened to d hat as opposed to d, right, or x. So, what we have is x of n. This is the system we tried to design. We have observed x of n. We want to design this filter, or we started designing this filter, and if we design this filter, the hope is that we have an estimate of d hat of n, d dash of n, which is close to the d of n, and we can see what happens in terms of this signal itself, right. This is a noisy signal or a noisy d of n, and then we want to see what does the filter do by removing this noise, right. So, if you think of in very high level signal processing, this is, say if there is signal and noise, we want to kind of increase the gain or increase the, this filter we want to increase the SNR. So, if there is SNR certain value here, we want the SNR to be higher at this output, right. That is what the filter is supposed to do if it is going to minimize the noise power, right. So, if you think of, so in this case it is useful to think of signal to noise ratio, right, which is the ratio of the signal power to the noise power. So, if we reduce the noise power, that means the SNR will increase, right. And so, let us just use some specific number just to get a value. So, this sigma v squared is assumed that it is unit variance white noise. Alpha could be any choice, but let us just take alpha happen to be 0.8. If it is this is the case, then before filtering what we have here is this x of n is d of n plus v of n, right, which means this is the signal power and this is the signal, this is the noise. The ratio of this is the signal to the noise ratio or noise power, right. So, if you assume this d of n to be of unit variance, then this Rd d0 is 1 and that is sigma d squared. So, if you look at this input signal, then they are kind of equal in power just based on our assumption. This power in d of n is 1, power in v of n is also 1. So, if your SNR is the ratio of 10 log ratio of this power, then you will end up that with being 0 dB. The input is 0 dB, that is the noise, that is the SNR of the input signal, right. So, now let us look at what happens after filtering. So, recall when we discuss about random process, you could think of this as a random process, this being a filter acting on the random process, and you have a desired signal, right. So, you can then relate this desired signal d, which is d dash, which is the output of this filter as a convolution of this w of n with this input signal d of n, right. So, if you expand this or use this to estimate what is this output power now, which is essentially sigma d dash squared if you want to, it is the mean of the square of this d dash of n. So, if you substitute for this d dash with this equation here, you have a summation as we had seen in the previous discussion. This will be thought of as a convolution, and you have a term which is expectation of d of n times d of n minus k, right. So, that essentially will be this RDD, these W transpose and W are our filters which we design. So we could use this W0, W1 as a coefficient, and RDD, remember, is just the desired signal, which is just an auto regressive process first order. So its autocorrelation is just 1 alpha 1, right. Similarly, the filter is W0, W1, we have it here. We could go ahead and substitute, do verify that this does turn out to be that way. What we will end up is, so this W0, W1 are like the ones which we derived in the previous sheet. Just plug in those values, you will see that this value is essentially something like 0.37, right. So similarly, we can do the same thing for noise, because if you look at this filter and if the input is noise, what happened to the filtered noise, right. So if you look at the filtered noise, then what you have is this WT again with B dash substitution, you will have this in terms of noise autocorrelation. In this case, it's unit white noise with unit variance. So this is just an identity matrix. So W transpose W is what you have. That turns out to be some approximately 0.22, right. If you plug in these values, you see that this output SNR is of the range 2.3 dB. Okay. So now you could compare this SNR after filtering, which is this, and SNR before filtering, which is 0 dB. Okay. So there you could see a gain of about 2 dB. Right. So where do we get this gain? We get this gain because of having designed a filter which is trying to attenuate this signal or remove this signal appropriately. What is this appropriate thing? The appropriate thing was trying to do was, it was trying to minimize this mean square error, right? Minimizing mean square error, right? This is what we did when we try to find the optimal filter to minimize this error, right? So essentially, by minimizing this error, we have achieved a improvement of about 2 dB. Right? So what this example just illustrates is, this is one specific way of using let's say Wiener filter to filter a signal. So there are many other applications such as noise cancellation, prediction, linear prediction, and so on. So any of these problems would start up with setting up what is your x of n, what is your d of n, how is x of n and d of n related, what is the length of the filter you are interested in, and more or less as the discussions we have been looking at, W is essentially assumed to be an FIR filter, right. So that hopefully this example will have given you some idea about how to use an FIR Wiener filter to do something more practical, as simple as just filtering to remove noise, right. It's we convinced that it leads to an improvement in SNR. So that kind of finishes what I wanted to say in terms of an example of an FIR filter. The last remark I want to make in terms of this Wiener filter is, so recall we had only looked at FIR Wiener filter, right. So but that does not mean this is only possible thing, but we can also have or an IIR or infinite length Wiener filter. So this is again this is saying that we are relaxing, instead of H being a finite length filter, we will have a H which is of infinite length, and in this case if you look at our if you look at x of n going through a filter and we have our estimated or desired signal d hat of n. If this is what we want, then in this case the way we would look at it is this d hat of n, instead of having a finite length, we'll have so it will be an infinite length filter which we would want to design. So the while we are not going to discuss too much about this, but only thing I would like to mention is the approach to do this would be through the Z transform domain or looking at the frequency response, because when we have this infinite length impulse responses, we could relate them more easily to Z transform or Fourier transform or their power spectral densities rather than just looking at the temporal domain. So again, when we talk about this IIR filter, there could be some specific cases where at times we are okay with a non-causal filter. So in this is usually the case when we are looking at images, so or image processing. So if you are interested in, you could look at this, how this is done, or could be a causal IIR Wiener filter, which is more probably practical, but this again involves some prior knowledge about some spectral estimation tools to understand better on how these causal IIR Wiener filters behave. Since we have not looked at these specific things, and in practice we don't use these too often, while this Wiener filter in images is much more popular and effective. For other application it is not as popular as in images. Of course, there are some speech enhancement techniques also which use this Wiener filter. Again, for want of time, we are not going to discuss these things. Hopefully, at some other point, we should be able to cover such things. So, this kind of concludes this continue lecture on the Wiener filter. Before we move on to the next lecture, which will be on adaptive filtering. Thanks.